Convert, Calculate, Cure, the math behind medical dosage.
By Whitney Roberts,
Austin Whittemore.
Bria Wilson,
and Topanga Spell.
So first we're going to start off with our introduction, then we're going to go into some history, then we're going to go into the calculations, and then feel free to ask questions.
Okay, so why are medical dosage calculations important? Because if you make a single mistake and overdose or underdose somebody, you could be causing more harm than you're actually helping. And if the mistake is bad enough, you could actually be presenting like a fatal mistake.
Now I'm going to get into the history. So here's kind of the time periods that we're going to cover. Alright, so I'm going to start off with 2600 BCE all the way to 100 CE. And this time period really started with ancient Egypt and ancient Greece. They used pinches and handfuls as their way to calculate medicine, which wasn't really accurate, but that's what they did. Then we go to Hippocrates II. He was an amazing Greek philosopher and physician, and he really pushed the idea that medicine should be based off of age and strength. And then later, Galen, he's a famous Roman doctor. He started to shape that early pharmacy and used drachriums and grains as his way of calculating medicine. Then we move on to the 1500s, which I like to call the big idea. So Paracelsus is a famous Swiss doctor, and he is also the father of toxology. And he said the quote that the dose makes the poison. And this is really, really important because if you can give a person medicine, of course, but if you give them the wrong amount or too little, that won't benefit the patient. So this kind of laid the foundation like, hey, we need to start focusing on calculations and being more accurate when it comes to dosaging. All right, the 1600s and the 1700s, I like to call the hustlers. This was the apothecaries era, and this is really important to Europe. This is when they started to take the medicines and mix them. They used scales for weighing herbs. They used the mortar and pestle for grinding. And this is a really important era because people were doing this for their jobs, to make money. They had patients. And this was really the early pharmacy era. Yeah. All right, Austin.
Okay, moving into the 1800s, this is the intro to standardized dosing. Before this time period, everything was based on tradition and like guesswork, but moving into this time period, this group of three guys right here, they created the US Pharmacopoeia, which brought drug names, ingredients, and dosages. It just standardized a lot of information. It's also very important during this time period, Europe came up with the metric system, and that is used for dosage calculations around the world. And also, during this time period, doctors began adjusting for children because they don't metabolize medicine like an adult would, so it's very important to give them a different dose. Okay, moving on into the 1900s. This is scientific regulation. In the 1900s, they learned how the drugs work chemically, which essentially means like, how does the medicine move through your body? What does it actually do? This led to a lot more accurate ways of dosing using weight and body surface area. During this time period, the FDA was founded, which brought guidelines for how drugs can be tested, labeled, and if they're safe to use. And this guy right here, that's Oswald Schmiedberg. He's known as the father of modern pharmacology. He helped turn this study into an actual science. He trained many young scientists who shaped the 20th century. Okay, and moving on to today, this is present age. With calculators and computers, everything is digital and everything is more precise than it has ever been. Drugs are no longer just tailored to you by your weight and age, but also genetics, organ health, and other medications you might be taking. There's so much that goes into a calculation. And this guy over there is Dr. Robert Califf. He's the current FDA commissioner, and he leads efforts in enhancing drug safety and is bringing a lot of improvement to this medical field.
Alright, now into the calculations. And for the examples we're going to show you guys, these are mainly going to be centered on pediatric medicine. And the reason behind this is, like Austin said, children do not metabolize drugs the same way adults do. They're not fully developed, and they're overall more vulnerable, which means they need more highly individualized dosages. Okay, the first way we're going to show you guys is using Young's rule, which is dosing by age. And this is mainly used when your weight and your height is unknown, mainly in over-the-counter medicines. And this is mainly more effective when the child is under the age of 12 years old, because at 12, that's when you would be considered an adult, like, for dosing. And this can actually be turned into a piecewise function where A is your age in years and D is your dose in milligrams. So if you look at the chart, it'll be 50 milligrams if your age is between 0 and 1, and 100 milligrams if you're 1 year old or older but less than 4, 150 milligrams if you're 4 years old or older but less than 7, and so on and so forth. And this is what the graph will look like. As you can see, like, the x-axis is the age going up, and then the y-axis is your dose in milligrams, and it kind of looks like a stair step. As you get older, you're going to need more because you're developing more, you're growing. And if you look at the top, after you hit the age of 12, you're just going to get the standard adult dose, which is why it kind of caps off up here. Okay, the next one I'm going to show you guys is dosing by weight, which the first thing you're going to want to always do is convert your measurements to the metric system. In the United States, we all use the imperial system, which is pounds and feet, but all over the world, the metric system is highly used, and it's the standard unit of measurement for medical dosaging. And the only thing we're really going to need to do for my problem is convert the pounds to kilograms, which is just divided by 2.2, since there are 2.2 pounds in 1 kilogram. Okay, the next step is to do your actual calculation. So you're just going to take your weight in kilograms and multiply by your dose in milligrams per kilogram. And then after that, you're going to divide by the frequency, which we're not always going to need to do, but mainly when you're going to be taking the medicine more than once a day. And then our last step is going to be convert to milliliters if you are taking a liquid medicine. Okay, my example for today is a child weighing 40 pounds is diagnosed with strep throat. The child is prescribed 30 milligrams per kilogram of penicillin twice a day. The medicine is available at a concentration of 350 milligrams per 5 milliliters. How many milliliters should be administered to this child? Okay, so the first thing that pops out of me is that 40 pounds that needs to be converted to kilograms. So we're going to divide that by 2.2. And that's going to give us 18.18. And if you look, Whitney's over there showing you guys how to do it. And then we're going to multiply by that 30 milligrams per kilogram. And that's going to give us about 545.45. And if you look at the problem, it says the child is going to be taking it twice a day. So we're going to go ahead and divide that by 2 so we can get the amount for just 1 dose. And that's going to give us 272.72, which is the amount of milligrams the child needs to take. But it is a liquid medicine, so we're going to need to find the milliliters. So if you guys don't know, the milligram is going to be the strength, and the milliliter is going to be the physical amount that you drink. So in order to get this converted into milliliters, we're going to take that 272.72, and we're going to divide that by 350, which is the concentration that it's available at. And then once we're there, we're going to multiply that by 5, and we're going to get 3.896. And what I did there is just take, like, the desired over half formula, which is commonly used in chemistry, to convert the milligrams to the milliliters. And the child's going to need 3.896 milliliters to get to their 272 milligrams.
Okay, so the next way we're going to do is using body surface area. So we use the Masteller formula to find the body surface area, which takes into account a person's weight along with their height. This will also have to be in metric units like Bria said. So the conversions we would do, we would get your pounds and you would divide it by 2.2, and that would give you your kilograms. And then you would get your inches and you would multiply them by 2.54 to get your centimeters. So for the calculations, that with the square root would be the Masteller formula, which gives you your body surface area. And then you would multiply, which is multiplying the weight and the height, dividing by 3,600, and then square rooting it. And then you would multiply by your dose per meter squared, and then that final answer would give you your dosage. So we're going to do an example problem. So a child weighing 50 pounds and measuring 3'9" feet has been diagnosed with leukemia. The oncologist has ordered cytarabine at a dose of 100 milligrams per square meter. What is the specialized dose for this child? So the first thing you're going to do is do your conversions. So you would do your 50 divided by 2.2, which would give you about 22.7. And then, and considering there's 12 inches in a foot, there's 45 inches and 3/9 feet. So you would do your 45 times your 2.54 to give you 114.3. And then you would plug those numbers into the Masteller formula, which Austin is doing right now. And then that, when put into the calculator, would give you about 0.849. And that is this child's body surface area, which then you would multiply by the dose, which is 100, to give you 84.9 milligrams. So that would be the specialized dose for this child. And that was our last example problem. So if there's any questions y'all would like to ask, y'all can do so.
I'm Catherine. And I'm Charlie.
And today we'll be exploring the history of math.
So as a group, we decided we first wanted to discuss the origins of mathematical thought. This includes the people, places, and processes involved in making mathematical contributions. Humans have been using math since before the first language was even created. Evidence shows that 50,000 BCE, humans used math to trade, count, and report animals. Primitive humans were also able to recognize patterns in their everyday lives and use mathematical thought to record their findings. For example, hunter-gatherers from the Ice Age made notches on bones to track the lunar cycle. These early stages of math discoveries are important, and without them, modern mathematics would not be the same.
Alright, now if you'll shift your focus over here to this screen where I will introduce you to the abacus. So this is one of the oldest known mathematical tools, and basically there's just a bunch of beads, and then each column represents a digit in the base 10. So like, if we say this is the ones place, we have 1, now it's 11, now it's 111. So what we're going to do is some simple addition. We're going to do 5, which is this separate bead up here, plus 6, which I'm going to get out of here. So we're going to add 6 beads total technically, but it's going to be a little complicated since we have to carry over, because 5 plus 6 is 11, as you guys know. So we have 1, 2, 3, 4. And then now it's 9. If you want to move up, then it's 10. So we have 1 in the tens place and then 0 in the ones place. And then you add your last 1. And as you guys know, 5 plus 6 is 11. And that is how you get to 11 on an abacus. Thank you. And now, for prehistoric math, before we had writing or numerals or language of any kind, we used to do like notches on random things that we found. And what happened to be the most durable was bones. So the first one on the top over there, you'll see that is the Ishago bone, and it was how many like strokes are on each one. It was probably used for simple arithmetics. And then the second one is the Lubongo bone found in South Africa, which is interesting because it has exactly 29 notches. So archaeologists believe this may have been like a month tracker or a lunar cycle tracker of some sort. And then the last one is the wolf bone of Doni Vespucci. So these notches on bones were technically like the predecessors of some sort to the tally marks that we use today, which are groups of 5. So we decided to interview our fellow GSE students about how they use tally marks throughout their daily lives.
All right, what's your area 1 and what's your name?
My area 1 is social science and my name is Hannah May.
So when was the last time that you used tally marks?
The last time that I used tally marks was whenever my AP class was trying to figure out who was our favorite teacher.
Perfect. Oh, thank you. What's your name and what's your area 1?
I'm Meredith and I'm in English.
When's the last time that you used tally marks?
At the end of the last school year, we played like games in class, and so we used tally marks to keep up with who won.
Very nice. What's your name and what's your area 1?
I'm Nora, natural science.
When was the last time that you used tally marks?
today picking which North Carolina state park was our favorite.
All right. What's your name and what's your area 1?
My name is Kelsey, and my area 1 is math.
Interesting. So when was the last time you used tally marks?
So during my AP exams, I tried to count how many answers I got A, B, C, and D for.
Interesting. Thank you so much.
So as you can see, despite the fact that tally marks are an ancient method of mathematics, they still have a variety of uses today.
Now, Mesopotamian mathematics dating back down to 3000 BC, where they use 60 base numbers, that's why we have our 60 minutes a day, and at 360 degrees in a circle. While they know basic geometry, algebra, and math. And on the next slide, these are some examples that Mesopotamia used back in the days. As you can see, as a cuneiform, that's where they wrote the inscriptions.
Now we're going to talk about Egypt. Egypt has been historically known as the intellectual center of the world. Whenever I was researching the history of math in Egypt, it became clear that there are two often overlooked mathematicians in Egypt that made really important contributions to math. One being a scribe named Ahmes, and the other a geometer named Archimedes. In 8000 BCE, humans first began using fractions as a way to tell time and measure angles. Later, in 1650 BCE, Ahmes wrote the Rhiine Papyrus. The Rhiine Papyrus, it was a scroll. Egypt used it as their primary source of mathematics, and it included methods of multiplication, division, algebra, geometry, such as ways to find the area and volume of different shapes. Later, in 250 BCE, Archimedes began building on Ahmes's methods using the papyrus. He calculated one of the most accurate representations of pi that we know today to be 3.14. He also devised a way to find the area of a curve under a function, which is taught in calculus. Two other things he introduced was powers of 10, which correlates exponents to numbers of zeros when multiplied by 10. So 10 is equal to 10 to the first because it has 1 0. 100 is equal to 10 to the second because it has 2 zeros, and so on and so on. He also formulated the way to find the volume of a sphere, which we know today to be 4/3 pi.
Alright, once again, it is your favorite part of the show. And if you look on the board here, there's this amazing graphic that I made from scratch. So, as Charlie just said, the Rhiine Papyrus written by Ahmes had a bunch of math in it, and they used it for the basis of all their calculations. So, if you'll move your attention to this board over here, Ahmes says that the area of a circle is equal to the area of a square with a side length of 8/9 of the diameter. So, somebody remind me, what's the modern day formula for the area of a circle?
Pi r cubed.
Pi
Pi r squared.
Pi r squared, that is correct. So I'm going to need some more help in solving this. We are trying to look for pi. So we're trying to get pi by itself. But there's two variables here that are kind of not the same. So how could we change that into a way that we can solve? Anybody shout out the square root of them? Square root of them? I would not do that so early because that gives me pi.
You can substitute D for 2R.
That's correct. Okay, if I did the square root, I would have to do too much other work, so I'm going to go with his answer. So 8/9 times 2r squared is equal to pi r squared again. And now if you want to take this square and distribute it into the rest of the thing, you are going to get 64 over 81 times 4r squared equals pi r squared. And now you probably understand why I went with that guy's answer. Because now you can divide everything by r squared. And now you can eliminate all of this junk. So now you have 64 over 81 times 4 is equal to pi. And this is pretty much equal to 3.1649. If you want to verify that, you can take out your calculator and make sure that I'm not lying to you. But this is a pretty close estimate of pi for the time that they lived in without calculators or anything
advance ancient civilizations were ancient India and ancient China. They don't receive near enough credit for the amount of work that they did to create advancements that we still use today. So in ancient India, they mainly made advancements in the realm of numericals. So one of the first things they did was find a method for finding the greatest common divisor. Some of you may know this as the UCF. So basically they used division in order to find what was the largest factor that two integers could be divided by. This is something that we've done in governor schools, so that shows how advanced ancient India was. Another thing that they did was they used negative numbers as part of their credit system. So previously in other civilizations, in money, you only had positive numbers. You couldn't go into debt. But in India, they introduced the idea of debt by using negative numbers as part of their credit system. Some of y'all probably don't like that. Another thing that ancient India did was they developed the number zero. So previously, nobody had really recognized the importance of zero, but Indian mathematicians recognized that if they were going to be able to solve algebraic equations, they had to have a number zero. They had to have the concept of nothing. And so Indian mathematicians accepted zero and embraced it, and allowed other civilizations to make advancements using this number zero. And finally, in ancient India, they developed a decimal place value system and rules for operations. And this basically just allowed for consistency as further mathematical advancements were made in other civilizations. And so simultaneously in ancient China, they began solving algebraic equations. These were mainly just basic one variable equations, stuff that you probably began to solve in middle school. However, in the ancient world, this was a big deal because previously math was just used for the sake of efficiency, like tracking things and stuff. But now ancient China was beginning to actually try to make advancements in math, like what could they be learning? And this was the first time this had been done. And then also in ancient China, they were making advancements in negative numbers, and they were including them in these algebraic equations that they were solving, and this would be furthered in other civilizations. And then finally, ancient China used proofs to prove that the algebraic equations they solved were correct. And this is something, once again, we are doing in governor school now, proving how advanced ancient China was alongside ancient India. And so in ancient Greece, you're probably much more familiar with some of their mathematicians, and maybe you've probably heard the name like Pythagoras or something. So this is unlike ancient China and ancient India. However, the main thing that ancient Greek mathematicians did is they used algebra to solve problems that had previously been solved using geometry. And so one example of this is the case of finding the height of the pyramid. So beforehand, they were kind of just, stacking stones, doing things like that in order to measure the height of a pyramid. But Greek mathematicians recognized that you could use the shadow of the pyramid in order to form a ratio with the pyramid in order to measure the height. So no longer were they having to go through the tedious task of stacking stones to measure the height of the pyramid. They could measure that shadow on the ground and be able to find the height much easier. Another advancement that took place in ancient Greece was the Pythagorean theorem. Many of you probably heard of a squared plus b squared equals c squared. And so Greek mathematicians embraced this idea as an algebraic method for finding the length of the hypotenuse, or one of the other legs of the triangle, instead of just measuring. And then that same concept was the circumference formula. So previously, they had just been measuring around this kind of circle, but they used the new number pi that Albert showed us how ancient mathematicians found. They used this to use the formula 2 pi r behind the circumference of a circle. And this made it much easier when we know some of the variables in the circle and allowed for future advancements in exploring the circle. And then finally, the Greek mathematician Eratosthenes developed the secret of Eratosthenes, which was a method for finding all of the prime numbers between two specified integers. And basically this method just involved crossing out all of the multiples of each number until you got down to all of the prime numbers. And this was a big advancement in the ancient world because it allowed them to find all the prime numbers much easier than just having to think off of their new calculations.
Last, the legacy of early mathematics. So as you can see in our presentation, we went through different types of ancient civilizations that help us shape our world today in technology, education, and science. Thank you.
Imagine you're the boss of a big, famous, and very expensive art gallery. The gallery is shaped really weirdly with several different walls and corners, so how do you go about hiring guards? That's what we're here to help you figure out. But we want to do it in which there is a way with no blind spots with the minimum amount of people. To solve this dilemma, you are given this weird-looking polygon as your floor plan, but what do you do from there? That's where we come in. With the art gallery theorem, we are trying to determine, when given a simple polygon and points with a view of 360 degrees, what is the smallest number of points needed to view the entire shape. In this presentation, we will teach you the equations and the math itself, including how to triangulate and tricolor the space. We will first go through a deep dive on the history, and then our beloved founder. We will hear from Dylan on the explanation of the math itself. And be sure to ask questions whenever you need to, because it can get a little confusing. Finally, we will be talking to you about why exactly should you be interested before we go into the interactive portion of our theory. Now on to Kate with how exactly did this come to be?
So our gallery owners wish to put camera in such places where the whole gallery would be seen and protected from thieves. Gallery owners need to figure out where the camera should be placed, how many of them, and what's the minimum amount. Luckily, Victor Klee introduced the idea when discussing with basic Chavarro. Chavarro designed a complex proof for the theorem, which was later made far simpler by Fisk. In our presentation, we will use Fisk's proof to solve this dilemma.
Our founder, Victor LaRue Klee, was born in September 1925 and died in August 2007. He was a mathematician who was a member of the University of Washington's mathematics department for almost 54 years. He covered convexity, functional analysis, the theory of algorithms, optimization, and pieces of combinatorics and geometry.
Klee was unique because he posed the algorithm problem to another mathematician in a very interesting way. For a simple polygon P with a specific number of vertices, and he asked, what's the minimum number of guards to suffice across every single P was? There might be fewer guards possible in some versions of P, but what matters in the R gallery problem is the number that is sometimes necessary but always sufficient.
So, how are we supposed to find a number of guards that works for every single shape in the universe with a given number of vertices? The first step is polygon triangulation. What this means is that we're drawing lines between the vertices of the shape to turn the larger shape into a collection of smaller triangles. The important thing to note here is that we don't want any of our lines to cross because that would create new vertices. If done right, then any polygon with n vertices can be triangulated into n-2 triangles. So here we have our large shape, which has 14 sides, and through triangulation, we've broken it up into 12 triangles, making sure that none of our lines cross each other. The next step is to three-color the polygon. All we do here is assign each vertex a color, making sure that no line has the same color on both ends. This ensures that each triangle has one vertex of each color. Finally, and it may take a few iterations, we want to count the color with the color that shows up the fewest number of times, and that's where we place our guards. So now we've three-colored our shape so that each triangle, and we see here that red has shows up 4 times, and that's where we place our guards to solve this theorem. And here are some other examples of what the arc gallery theorem looks like. So on the left, we have another triangulated and three-colored shape, and on the right is an example of what it looks like when we describe how the area that each guard can see. So we've covered the steps to determining optimal guard location, but how do we represent this mathematically, and why exactly does it work? Well, for the formula, we assume that our polygon P has some number of vertices n, and in doing so, we get the equation g of n equals floor of n over 3, where g of n is the number of guards as a function of the number of vertices. Floor of n over 3 tells us that we divide the number of vertices by 3, and then round that number down if n isn't divisible by 3. Here's the proof for the formula. After triangulation, the polygon is composed of triangles, and after 3 coloring, each triangle is seen by every color. Thus, choosing one color to place our guards on guarantees that the whole shape will be seen. Furthermore, dividing n vertices by 3 colors represents the smallest number of guards that can possibly cover the whole shape based on the given triangulation. Since every simple polygon can be triangulated, if n isn't divisible by 3, then it likely just means that one node of color covers more triangles, and the quotient can be rounded down to find the correct result. Finally, floor of n over 3 gives us the minimum number to be sufficient across every shape with the given vertices, meaning that there may be more efficient ways for some select formations of that shape.
Alright, to illustrate this point, we can take another look at a 14-sided polygon presented previously. By this formula's logic, 14 divided by 3 is 4 point something, which then rounded down gives us 4. This is supported by this version of triangulation. However, when we triangulate slightly differently, the coloration changes and we find that it's possible to cover the image shape with a minimum of just 3 guards. So for this example, 4 is the maximum number of possible minimums across triangulations of all 14-sided shapes. Therefore, this is the solution to the art gallery theorem for all 14-sided polygons. However, it can be done more efficiently in certain cases. So now you may be wondering, how can this actually be applied to the real world in our daily lives? First, surveillance drone, surveillance and security camera placement. Let's say you're trying to monitor a building, a museum, or any large facility. The goal is to install the fewest number of cameras while still covering every important area. Using certain algorithms, this can be done efficiently. Next, we have robot motion. Whether it's robot vacuum or surveillance drone, planning how it moves is key. These methods help us design paths that save battery, reduce unnecessary movement, and help robots navigate complex environments effectively. Finally, computational geometry itself plays a foundational role in fields like image editing. For example, if you need to calculate where to place lighting in a virtual scene or adjust parts of an image algorithmically, this type of geometry helps power these tools. So whether it's physical security, robotics. Okay, so the answer to what you guys are trying to do is the max was 4 guards, but it's still possible to do it with 3 guards if you kind of like manipulated the symbol a little bit. So raise your hand if you got it. Thank you for listening to our presentation.
Before we start Papapalooza, who here thinks popping bubbles is relaxing? And who finds it weirdly stressful when that one bubble just refuses to pop? Exactly, this is basically group therapy. Welcome to Papapalooza. My name is Alicia.
My name is Kelsey.
I'm Najira.
And my name is Maria.
So here's our agenda for today. We're gonna start off with the intro, and then we're gonna go into the game Papapalooza, development, and then play. A brief introduction into game design is it's basically the process of creating and shaping the rules, mechanics, and the overall experience of a game. I'm pretty sure, I'm like 99.99% sure that all of y'all play a game here, so.
Sure guys, Block Blast counts. So what exactly is our game? So Papapalooza is a bubble shooter game where you have a grid of colorful bubbles and you have one shooter bubble at the bottom. And the goal is to aim and shoot the shooter bubble at the grid and match the colors to make them pop. And the balls continue moving downwards, and so the goal is to pop as many as you can before they reach the bottom, and then you lose. So our game is really engaging and fun because it's simple, yet it's exciting. It's easy to understand, but it's challenging to master. It has vibrant colors, appealing bubble designs, and high quality graphics. So these are our original designs for what we wanted the game to look like. We created these images on Canva, and like all projects, our game does not look like this, but it helped our inspirations on building the game.
So now we're going to move on to talk about the development of the game itself. Starting with logical statements, these basically help determine whether a statement is true or false. This is present in almost every piece of code, and it basically helps create an action and reaction relationship, which helps fuel the environment of the game. So a conditional statement would be a perfect example of that. Over here, it says, if a launch bubble makes contact with a bubble on the grid and it's the same color, the bubbles will pop. This would be a biconditional statement because both of the statements need to be true for this to happen. Technical difficulties, 1 second.
That's great that that happened during ours.
This side.
Okay, we're back.
this is basically just saying that collision is an illusion. Technically, if you threw a bubble at the bubble grid, it could just like fly through it. So this basically just says that we need to create an illusion of the bubble hitting another bubble.
Okay, so next up is the coordinate system. So the coordinate system involves of x and y coordinates, the same ones as we use in our math class. So as you can see, the game background is a graph of a coordinate system. So each position on that graph holds the bubble's location. The bubble's location is determined by the coordinates on the graph. So as seen in the picture right here, you can kind of see how it looks like a graph. So basically, the shooter bubble, the red one at the bottom, when it hits another bubble on that graph, the game will then check if it intersects with the coordinates of the graph. If so, that bubble would end up popping.
So video games will be pretty boring if the same thing happened every time. So because there's little skill involved in just memorizing a pattern. So video game developers use RNG, which is basically a random number generator. So a random number generator basically generates a random number, and that value will be set to a certain characteristic. So for example, in our game, we used the RNG to randomize the different colors of the bubbles, because then you can have a different gameplay experience each time you play. So here's kind of an example of our code and where we use the RNG. So if you look at the purple block, we picked a random number between 1 and 3, 1 being a red bubble, 2 being a yellow bubble, and 3 being a blue bubble.
So what are some positive impacts about mobile games? So first, it enhances problem-solving skills. So the player during the game can make decisions, strategize, and plan during the game. So such as our game Papapalooza or other games as chess or tic-tac-toe. Secondly, it enhances cognitive skills. So the player cognitive abilities is like attention and focus and memory foundation. Then it enhances memory. So games such as memory cards allows your memory to be sharpened and for you to retain more information. And it's also a mood booster. So when a player is playing a game, it allows them to have a sense of achievement when they complete a goal, and it also gives them a mental break from our daily stressors. And then lastly, it is an inexpensive environment.
How is stress relief seen in playing popping games? So it basically has simple gameplay. It has straightforward goals, match and pop the bubbles by color. It's like giving your brain something light but focused to do. The act of aiming and bursting colorful bubbles can surprisingly be soothing and calming, but I tend to get stressed when the red color isn't coming out and I quit the game. There's also a dopamine boost when you're playing the game. It engages with the player, it has soothing background music and popping sounds. Now, we're gonna give y'all a little demo of our game. This is our current leaderboard. Kelsey is a tryhard. I don't know how she got 2,000.
Only 200 more than Maria.
Okay, both of them are tryhards. Me and Padira kind of gave up.
So I'm gonna try to beat my high score right now.
Yeah, we're gonna give her another shot. Yay! So you have to press the green flag to start.
It works, I promise y'all.
The colors. And here we have reflection. Whenever she hits the side, it reflects to the other side. Yeah. We have another example.
Can y'all tell why I didn't get the high score?
You're doing great.
Thank you.
Okay.
I lied.
You're beating your high score.
Okay, she did beat her high score, yay. Okay, and then obviously the bubble is reaching the bottom, and then game over. Now, are y'all ready to try and beat the high score of 2,409? Scan the QR code, and whoever gets the highest score by 840 will get a special prize, one of a kind. So y'all have 4 minutes. If y'all have any questions, y'all feel free to ask. We're here to help y'all out.
Yeah. Y'all are doing great.
Thank you.
Any questions? So we started our Cornerstone project like on day 2 of GSE. The actual coding part took basically like 2 weeks.
So we started by using GDevelop to make the game, but it just got really complicated since we didn't know the software too much. So we had to switch over to Scratch. And honestly, I probably spent like at least a solid 2 or 3 hours on GDevelop trying to figure that out. But Scratch took me about the same time, but I actually built it this time. So.
Well, she did like build it like very far, but then it just kept on crashing and crashing and crashing, and I think she almost took her computer. Oh, please don't throw your phones if you get stressed. Okay, guys, y'all have 2 minutes. 2 minutes.
Who's died already?
I have. I didn't see the ball on the side.
Okay, any more questions?
I've coded a bit, but not enough to say I'm an expert at it. Any more questions? Yeah.
How long did it take you to get 2,000?
Okay. I think this was like yesterday. I started playing halfway through lunch because I got bored, and then all my friends left, and then I just sat there and kept playing until they kicked me out of the dining hall.
She texted us, like we have a group chat, she was like, guys, I got 2,000. And I was like, what the heck?
And then Maria.
I think I probably took about 20 minutes to get it, because I was done with the presentation, so I was just testing the game out to see if it actually works.
Yeah.
Hajira, how long did it take you to get 34?
I think it took me like a solid 30 seconds. But I did my best, guys, I promise. You saw how bad I was.
Okay, we have 1 minute left. Who's still playing? Okay. Okay, it's 8:40. Somebody tell me your score. You have to stop.
330.
1583. 221.
Okay, I heard 330.
1600.
What? 1600? Go Chelsea.
1597.
What's Chelsea's score?
1605.
65.
I'm at 1161.
Nowhere near.
I'm at 184.
You actually have 1600.
Okay, so we have our winners. Special, unique, one-of-a-kind prize is bragging rights to Papapalooza. Thank y'all so much for hearing us talk about our game. If y'all have any questions, we're still open. And yeah.
That's it. Yay!
return rate, sorry guys. After 5 years, your estimated amount of money will be $1,640. The profit you make is $640, and capital gains tax 50% on $640, which is $96.
So the next thing we'll be talking about is company stock. The company we chose is Tesla. Tesla was founded in 2003. Elon Musk joined in 2008. Their current stock value is $315.35. They specialize in renewable energy, especially electric vehicles. So when you invest in a company, you're only buying a small portion, and your profit is determined by whether or not they are increasing or not. So if a tweet from the CEO comes out and their stock decreases, so does your money. So I created this Desmos simulation that shows the Tesla stock between 2015 and 2025, and it shows the market trends. And so you want to buy when it gets lower, so like right here, and you want to sell when it goes up, which is not doing, but there. When you do that, you want to sell, and that's when you get the most profit. So the taxes is paid basically like regular income, but only if you held the stocks for less than a year, and it will be taxed at 4.2%, which is normal income in North Carolina. But if you had the stocks over a year before you sold it, it'll only be taxed at 3.99%.
Okay, so the next type of investment we'll be talking about is real estate investments. And to invest in real estate, you can buy houses, apartments, buildings, or even land. And to gain a profit from these properties, you can rent them out to tenants, and the tenants will pay monthly rental payments, and that will be your form of payment and income. And then the second way is something called property value appreciation. And this is when you hold on to your property for an extended amount of time, and then over time that property will gain value, and therefore your investment will gain value. And when you sell it, it'll be worth more than when you bought it, so you'll be gaining profit. And then the third way is to buy undeveloped land with the goal of it being developed in the future. So this could include new houses, new parks, new stores, anything like that, because people or investors that would be buying it off of you will most likely be buying it at a higher rate than when you bought it, and therefore, once again, you're making profit. Okay, and then when you tax your profit from your real estate investments, there's two different ways you can do it. So when you're gaining rental income from your tenants, it's taxed through income tax. And this is just regarded as normal income. And so for this example here, if I collect $18,000 a year from my tenants, and I have to pay $8,000 to maintain the property, I'll be left with $10,000 in taxable income. And if I fall in the income tax bracket of 20%, then I will be paying $2,000 in taxes off of the money from my tenant. The next is when you sell your property for profit, and this is called a capital gain, so you use the capital gains tax rate. And this is determined by two factors. One is how long you've had the property, and the second is your income. So in this example, say I sold my property and I got $100,000, and if I owned it for over a year, I would be paying long-term capital gains tax, which is often between
capital gains tax.
Company stock at 300.
This is how long-term gains from a company stock are taxed. Okay, this is how short-term gains from a company stock are taxed. First person, raise your hand.
This is how short-term gains from a company's stock are taxed.
You gotta read it into your phone, right?
What is higher rate? No, okay, wait, hold on. This is how short-term gains from a company's stock are taxed. What is fraud?
Good evening, everybody. Thank you all for coming to our Cornerstone Machine Learning from Pixels to Predictions. I'd just like to thank the math department of USC and our fellows for making this possible. I'm Kelsey Everhart. I'm Shivani Mukherjee.
And I'm Alex Martinez.
So it's kind of vague from the title, but we made an AI model that can basically predict images and classify them. So it's a convolutional neural network. So before we get into the convolutional aspect, I'm going to give you guys some background information on a neural network. So these are artificial intelligence models that mimic neurons in the brain. So each of these like little circles here that you see, these are called nodes or neurons. So on the very left, we have the input layer, and this is going to receive the raw data, such as like images. Oh yeah, in our case images. And then on the very right, we have layer 3, which is an output layer. So these are going to output prediction or probabilities that predicts what image is. So we have 10 output layers, 10 output nodes, excuse me. Each one of those nodes is assigned an image class. So one of those nodes is like a frog, one's a ship, so on and so forth, because we can predict 10 total images. And then where the computations actually happen, that is in the hidden layer, or hidden layers. So here the neurons are used to recognize and categorize patterns. So as you guys know, images have like multiple things going on. We'll look at an image and immediately know it's like a frog, but you have to break them down first. So that's what all those layers are for. We have 11 layers, but there are obviously a lot more. So ChatGPT has 96 layers, and massive. So each one of these nodes have assigned weights to perform calculations. So these weights basically say how important each characteristic of an image actually is. So for these things to learn, to be able to properly classify images, there are two ways they train. This is with forward and backward propagation. Forward propagation is essentially running the program like normal. It's mainly to set up
10% chance of being a dog and 70% chance of being a zebra. And I'll pass this on. Oh, actually, code. So here's how it looks like in our code. Up top, we have the convolutional and max pooling layers. Under that is the image flattening, the bends, and the softmax layers, which we'll get into more code later. And now,
So, I'm going to briefly talk about how we train our model. So, just some background information. The data set that we used was called CIFAR 10, and it's split into two kind of main groups. So, one of them is the 50,000 training images, and the other one is the 10,000 testing images. Our model, when we run it now, it pulls from the 10,000 testing images group. And the other two things I'm going to explain are the pre-processing steps. So I'm not going to go into too much depth there, but that is an actual snippet from our code. And so what we did first is we normalized our pixel value. So if you're wondering why we picked 255, it has to do with RGB, and 255 just includes all the colors. And we also flattened our labels to increase our compatibility. And as for data augmentation, so we added image data generator over here. So again, this is another snippet from our code. And we added rotations, horizontal flips, and width and height shifts so that the model would be able to read the image better. And it also would prevent overfitting. And if you're wondering what overfitting is, I'm actually going to go into it a little more in the next slide. But just kind of a brief overview is that overfitting is when the model interprets the tiniest details in the image. So, and that also includes a lot of noise. And so that way, its predictions can go wrong. And then as for our model training settings, so this is the main training block that we have, and that includes our optimizer. So that is what is constantly updating our model parameters by adjusting the learning rate. We also have our loss function, which is what I'm going to go into more in the math section. It has to do with a lot of calculus. Metrics, batch size, so that all has to do with the number of training samples that we give it, as well as our toolbox. And again, we bring up overfitting over here, and that has to do with early stopping. And so early stopping is what we implemented in the code so that the model would stop once the model notices that it stops moving, it would not go any further. And if it does, that will mean that it's heading towards overfitting, which is basically, again, when it learns the data too well, it includes stuff like noise and small fluctuations in the image, which prevents it from giving us an accurate guess. And this is an actual screenshot from our code. It includes all the settings that I talked about before. So again, we have steps for epoch, the number of epochs, we have batch size, and all of that, as well as our early stopping over here. So last but not least, we also made sure that we were going to monitor our model's performance throughout the training. And so specifically, we tracked accuracy and validation accuracy. And so accuracy was specific to our model, validation was more general. And we also used, again, early stopping. So we saw that a couple slides ago. And so again, that just helped us prevent overfitting. And we also implemented this restoration of best weights. So that just means that after the model, so patience equals 4 just means that after the model doesn't, like if the model after 4 epochs stops moving, it's going to stop right there and it's going to go back and look at the best weights that it had, and then it's going to use those to make our prediction. And over here, we also
output. And a little example of how that looks like, if all it's doing is looking for borders. So it's just, this is the edge filter, and here's the image patch, and it's just looking for borders. Here's the rule change right here. That's basically all there is to it. And this is exactly the same. These filters help the CNN detect patterns like outlines of shapes or objects. For example, an edge of a cat's ear or the border of a road sign, so the model can understand the images better over time. Other linear algebra concepts used: it's matrix, multiplication, tensors, and flattening. Overall, linear algebra helps CNN strength by process and transform image data by using matrix operations like dot products and convolutions. The model can detect patterns, edges, and textures, which are the first steps in understanding what's in the image.
So now I'm going to briefly go over the calculus behind this. So mainly the calculus is involved in how the model is going to learn. And so I previously mentioned in training the loss function. And so that just kind of evaluates the model's performance by measuring the amount of loss, basically. And so this is the image. It is, the formula. And so this is rooted in calculus. And we kind of define what y sub k and p sub k are, but this is the formula for a multi-classification problem with k classes. And this is an example of how it would actually look like, how we would use that formula to calculate our loss, and we kind of sometimes refer to this as cross-entropy loss. So this screenshot over here is an actual image from our model. So our model was able to predict images correctly, so it predicted a shift in this image as a shift. But this is a separate example. This is just to show you how we would use the equation. So here you can see that the model is 40% confident that it's a fraud, and so we plug it into the equation and we get 0.916 as our loss. And so just a summary, there's a lot of differentiation involved in convolutional neural networks, and that is a key concept in multivariable calculus. Other places where it's used would be gradient descent and backpropagation, but in this presentation we just focused on cross-entropy loss. And so now we're going to look at a model. So the picture I got or the number I got actually corresponded to a picture from the 10,000 in the data set that we used. So picture 1,726. It was a deer, and our program predicted that it was a deer. So it's correct.
So hi, I'm Sarah Nichols. I'm one of the math instructors here. Thank you so much for coming to the Math Cornerstone. Quick word about how this is going to work. We have 4 different rooms with Math Cornerstone projects. Each presentation is about 15 minutes. So there's 4 time slots of 15-minute presentations with a 10-minute transition in between. So after this presentation is done, you are welcome to stay in here, look at the schedule, and go visit a different room. You'll have about 10 minutes to move between each one. So I'm going to stop talking so we can keep this moving, but thank you so much for coming.
Thank you guys so much for coming out here. My name is Lance.
My name is Subhan.
My name is James.
And my name is Colin.
And we are going to be your first mathematics group for this Cornerstone project. Alright, so the topic that we were given was machine learning. We were told to understand how machine learning works, the mathematical algorithms that underlie them, but for fun, we also built some machine learning models. But that's a really broad topic, machine learning. How did we make it specific? Well, we went into the housing market and we built 3 models that could predict your house's price both now and 5 years, 10 years, 100 years into the future. Alright, let's hit it. If it works, that is. If it works. It's a very big question. I'm gonna just stand here awkwardly. So my laptop just broke, which is very unfortunate. Mirrors to the screen. This is rather unfortunate. So before we go into into the machine learning or the math or any of that, let's talk about the housing market, because it's very complicated. How a house's price is determined isn't really like a defined number. It's really just a compromise between what the buyer wants to sell it for, or what they want to buy for, what the seller wants to sell it for. So there is no real way to get the number, but we can estimate it through something called hedonic pricing. And that's when you take a series of non-environmental and environmental factors, and you merge them together in a big equation to kind of find out what the house's price is. So an example of a non-environmental factor would be like the house's size, the amount of bathrooms, or maybe how old it is. And an environmental factor would be the location, the crime rate, or maybe pollution in the area. And if you take all these factors and put it together, you can kind of estimate the price of the house. That's what we did for our models.
Now let's get into some more information about the project, such as what was our goal, what data set we used to train the models off of, and the three type of models that we trained. And at first, our main goal of the project was to predict the total sale price of houses using machine learning. And for this purpose, we trained our models off of Wake County real estate data, and we trained three different models: linear regression, random forest regression, and XGBoost.
All right, so let's take a look at actually understanding our data. So for our data, we have a huge data set, right, of over 250,000 houses in Wake County. That's a large amount. Wake County itself actually has only 400,000 houses. So our model was pretty big and it had 250,000, which is over the actual half of it. Our next one was features. So features was more about things like the parameters that our model works around. So things like heated area, bath, your lot size, the year of build, the zip code, the city. All of those are things that kind of go into our model so we can get our predicted target price. And our target price is just essentially our total sale price. So that's at the end of the day, that's just the dollar amount that we're looking for. The final one is some of the challenges that we had with our data set. So our data set had something called a right skew, meaning that a lot of the values were at the left side of the data set, meaning that a lot of them were very low, around like 150 to 200,000. And that kind of skewed our data set, because when we were trying to put in values over 700,000, over 800,000, stuff like that, it would get very confusing. Like our model wouldn't know exactly what to do. Oh, sorry, yes. Pre-processing. So when we look at our model, right, we have a lot of data. We have, like I've talked about, 250,000 houses. That's a lot of houses. Not all of them are going to be like in perfect condition. Not all of them are going to have like the bathrooms, like all of them in the data set that are going to be like listed. So the first one that we use is conversions. So that's just essentially converting stuff like 3.5 baths, like in our columns, if it's written as 3.5 baths, we can convert that into just 3.5 itself. So we can convert that into the string. And the reason we do that is for our model, it can easily put it into the whatever math it has to do and come and convert it back. Our second one is one-hot encoding. So that's essentially just transforming categorical data like our zip codes and our city names into binary columns. And this is just so that our mathematical model can convert them easier and just work with it. Our next one is log transformations. So like I talked about earlier, we have a right skewed model. So we use these log transformations on our model to kind of even that out. So this kind of helps with that. Our last one is scaling numeric features, which I'll talk about on the next slide as well. But essentially what that does is just helps everything have a similar range. So if you go to our next slide, we have our heated area in square feet. And before scaling, you can see that it's ranging from above 4,000 all the way down to 1,000, 1,500. So that's a huge scale. If we look at our second one after scaling, we have a standardized value the same, and we have from -1 to 1. So that's way smaller, and our model can understand that way easier.
Alright guys, let's jump into our first model, linear regression. Most of you guys have seen something like this in math class. You have one x variable or input, and you get one y output out. So why would we need machine learning to do something like this? Well, what happens when we have multiple inputs? Let's say in this example, I wanted to find how age, health factors, lifestyle, and gender all influence shoe size. That's a lot more complicated than just finding height. Here we have our linear equation. It's made up of a set of terms, and each term has a coefficient or x variable. The coefficient depends on how important that variable is in predicting the price. Basically, the larger the coefficient, the more important that variable is. A linear regression model is very easy to train and simple to understand. However, it is not good at showing non-linear relationships. As you can see in our graph, our model severely underestimates the actual price of our housing market. This is why we decided to implement a second regression called a random forest. But before I dive into that, we must first understand what a decision tree is. A decision tree is a set of yes or no questions that divide the data into a predicted outcome. As you can see in this example, I want to know if I should go into the quad today. This decision tree can help me come to this conclusion. However, a simple decision tree like this is biased, inaccurate, and ineffective because it's so generalized. That's where a random forest regressor can come into play. A random forest regressor is a set of decision trees that take all the outputs of the decision trees and average it to make a final prediction. This shows nonlinear relationships well and is much more accurate than a linear regression. However, it's harder to see how independent variables affect the premise.
Alright, great. So we got linear regression, we got random forest regression, but unfortunately they didn't meet our standards. We still wanted a more accurate model. And that's when we went to the wondrous XG boosting model. The great thing for us is that it's really similar to random forest. It actually uses the same methodologies and the same math. The main difference is how these metaphorical trees are planted. In random forest regression, what you do is you plant all the trees at the exact same time. So although they can grow and learn, they do it all together. They don't learn from each other's mistakes. However, with XG boosting, you plant each tree individually. So after it's grown up, after it's learned its mistakes, and you've seen all the faults and shortcomings of it, you can fix those in the next tree you're going to plant. That way, theoretically, the last tree that you plant should be the most accurate tree you could possibly plant, because you've already corrected all the previous faults and shortcomings. Alright, now that we've done our three models, let's talk about the math that goes behind them. So, the math that goes behind them is pretty much trying to optimize the MSE, also known as the mean squared error. And that's just a statistical method to find how accurate your model is. But before we go into that, you need some calculus. So, do any of you not know what a derivative is? If you don't, just raise your hand, it's fine. Alright, great. So a derivative is a calculus method where you find the instantaneous rate of change on a function or an equation. So you can think of it as the slope of a function at a specific point. For example, if you have a y equals x squared, imagine you draw a tangent line to that graph. As you increase x, you're also going to see that tangent line increase because your slope is increasing. For example, if you look at this graph up here, you're going to see that at that specific point, that line is going to be horizontal. That's because the slope is 0, or in other words, the derivative is 0. And this is really important because as you can see, at a local minimum or a local maximum of an equation or a graph, you're always going to see that the derivative is equal to 0. So what we can do is that by finding when the derivative of the function is 0, we know where the local minimum is. And that's really important in the context of our project. Because when we find the local minimum or the 0 derivative of our function earlier, we can find exactly when the MSE is as low as possible, thus optimizing our equation.
Now let's get into some metrics that we use to evaluate the performance of our models. Up first is MAE, which gives us the average difference between our predicted and actual values, which gives us an easy to interpret method of understanding the accuracy of our model. Up next is RMSE, which is like MAE, but punishes larger errors more harshly. And the third one is a more common one, R squared, which shows how well our model explains the variability in the data using a metric from 0 to absolute value of 1. And then finally is MPSE, which gives us the difference between our actual and predicted values as a percentage instead of a value, which allows us to compare our models of different scales and currencies.
Cool, so now let's look at our actual comparisons between all three of our models. So first up, we have our linear regression model. And if we look at our MAE, like James was just talking about, XGBoost actually has the lowest one with 61,000. So again, what he was basically saying was the lower it is, the better it is, right? That more accurate it is to the actual prediction of the house. Linear regression, on the other hand, is 74,000, which is not that good at all, if you can't tell. Then we have RMSCE, and XGBoost came in at 120,000, but you might notice that random forest was actually lower at 106,000. And this was due to more hyper-tuning for random forest rather than XGBoosting. This kind of just came down to time constraints and kind of got lazy at the end. I don't know. But yeah, XGBoost, if we can talk to the next slide, is the best. XGBoost was by far the most accurate based off the MAE and both the RMSCE. And second place goes to Random Forest, which is a very close relative, like Lance was talking, to XGBoost. It was very efficient, it was pretty fast, and it kind of modeled the housing market in a way that third place, linear regression, couldn't. Linear regression is a really simple model, like we talked about earlier. We showed you guys the equation for linear regression. The housing market really isn't why it was I'm supposed to be. Like, I can't just put in two variables and be like, oh, boom, that's my house price, you know, like I can't do that. So that's why it's not the best.
No, this study wasn't perfect. There's things that we could have did better and improve in the future. For example, we used a very limited number of features. You can't really determine your house value just off its size, the number of bathrooms. There are much more other things to consider, such as how recently was the house was renovated, and other metrics that could improve the mall's performance. And next, another thing we probably could have done is put more effort into hyperparameter tuning, which could optimize the training process and allow us to make better models. And another thing we probably could have done is train on a larger data set than simply just Wake County, such as training on the data sets of all the houses in North Carolina, or on all the houses in the East Coast, etc. And finally, we in the future we would probably explore how the model makes certain decisions and to get a better understanding of what's going on under the hood.
All right. Thank you guys so much. If you have any questions about like the math, about the machine learning aspect, about the models, ask them now. We're open down here. Nice. All right, cool. Oh, we have a question back there. Ashley, what's your question?
So on the interpreting data slide, is there any reason why for one of the things is like 50% error?
Oh, that's a great question, Suhan.
All right, so infinity percent, if you can go back to the slide, I can point it out. All right, so take a look at our results again, right? So you're talking about the MAPE on this side. So again, the closer MAPE is to 0, that's the better it is. So for XGBoost, it was 16.4, which is pretty good. For linear regression, it was 61, which is pretty bad. Random forest was infinity, just because how random forest works, right? Like we talked about earlier, random forest has decision trees. In our model that we actually had, we had over 100 decision trees running at the same time. So the reason our MAPE didn't work was literally because it couldn't. Like, it was so too much kind of to process. On the other hand, XGBoost worked because XGBoost runs a different algorithm. It still has decision trees, but it still runs a different algorithm compared to random forest, just to make it a little bit quicker. Does that answer your question, Noel? Cool. Any other questions? Cool. Oh, all right, what's your question?
I was gonna ask for like random forest and XGBoost, you have to make those yourself by programming, or you're using existing software?
So that's a good question. So XGBoost and random forest, like I talked about, are something that already exists. So there's stuff called packages and imports from Python that you can use. But like all the math that is already done for you, you just have to kind of implement it into your own use case. So it still takes a lot of coding. It's not like I can just chat GPT, hey, give me a random forest model. Thanks. Like I can't really do that. So yeah, you still have to use your own mathematical skills and everything, but there's still a lot of stuff that's pre-built in for you. Any other questions? Yes.
Machine learning is kind of a pretty broad topic. Why did you guys decide to focus, I guess, on housing?
Mainly because there's a lot of data about the housing market. Machine learning relies a lot on just having a vast quantity of data to train the model. So we knew we were going to find a lot of data within the housing market, so we just kind of went there. And it looks like we are out of time, so if you have any questions, come up to us later. We were also going to show our model to you, but unfortunately the Wi-Fi here sucks, so we can't. So if you want to find out what your house is worth, according to our models, or what it could be worth in 10 years, come up to us, we'll be happy to try it out. All right, thank you guys so much.
All right, we're going to start the next talk. This is one of our groups talking about the prisoner's dilemma.
What's up, guys? My name is Jack.
My name is Anna.
My name is Desire.
My name is Courtney.
And my name is Emery.
And we're going to start off by kind of describing what we are doing. So we're going to start with a little game. I need 8 volunteers to pick from. And so that we're not expecting. Okay, Dimitri? We'll go with the striped shirt. You?
Wait, I'm in stripes. Wait. Can we both go? No,
Nah, just one of y'all. Y'all figure it out. Barrett, come on. Carlos, come on. You in the very back. I'll get to the back row. You come on. That's 1, 2, 3, 4, 5. What? You in the green shirt. Lance, come up and stay. That's 8, right? 1, 2, 3, 4, 5, 6, 7, 8. That's 9. One more girl.
Alright, so everybody partner up. Alright, we need one more person.
One more. Two more.
Alright, so everybody partner up and come stand face to face with your partner in 5 groups. Alright, so we're going to play a game called Split or Steal. You and your partner are competing for 2 pieces of candy, and you can either choose to split or steal. If you both choose to split, you both walk away with 1 piece of candy. But if one person splits and one person steals, the person who chose to steal gets both pieces of candy. But if you both steal, nobody gets anything. You guys have a minute to talk to each other and convince each other what you're going to do. But yeah. Alright, time is up. Alright, I'm gonna go around group by group and see what you guys put. Alright, each of you hand me a card and don't let the other person see what you hand me. Alright, you guys split, so you both get a piece of candy. Alright, let me see your cards. Don't show the other person. Alright? Alright, both of you split. You both get a piece of candy. Good job. Good job. Alright, let me see your cards. He stole. He gets both pieces of candy. Alright, y'all split. Y'all both get one. Alright, last group. Let me see. Excellent, good job. Thank you guys.
I just gave my candy away like, oh, I didn't want it. Well, I don't know what she asked me for it. I said,
So this is a game of the prisoner's limit. The prisoner's limit is a non-zero sum game, which means that players are trying to maximize their rewards, and they don't necessarily have to be the other person. That's what non-zero sum means. It means that it's a game that people can both play where they, like, their gain doesn't directly correlate with someone's loss. And so the common prisoner's dilemma is usually involved with jails, and it usually ends up with, next slide, with practices of people committing crime together and getting called into police stations and having to what was it, one-on-one? Yeah, one-on-one, talk with a police officer, and they get the opportunity to either rat their partner in crime out or cooperate and defect and don't say anything. And it can end up with different situations where if they both cooperate, they both spend 1 year in prison because they don't say anything, they don't rat each other out. If one of them cooperates and doesn't say anything, and one of them defects and talks against the other person that defects gets out for free, and the person that cooperated gets 5 years in prison. That can work both ways depending on people. And if they both defect and go against each other, then they both end up spending 3 years in prison. So it results in a loss for both of them if they go against each other.
And more of a real-world example conducted by the Journal of Economic Behavior and Organization. They took a real prison and a class of college students, and the real prisoners were more willing to cooperate than the college students on a basis of 55%, 37%, which kind of busts a stereotype you might have about prisoners.
Alright, after learning more about the prisoner's dilemma, we determined that our hypothesis would be when testing boys against girls, boys would be more likely to steal, and when testing friends against strangers, strangers would be more likely to steal.
So for our experiment, to test our hypothesis, we decided to go around campus and we played the split or steal game with pieces of candy, just like you saw earlier. And then we grouped up between boys and girls, and we made sure that the boys were either friends or strangers, and we also made sure the girls were either friends or strangers.
Alright, so after tallying up the governor's school student results, out of 24 people, 2 boys that were friends split while 4 stole, 2 boys that were strangers split, 2 boys that were strangers stole while 5 boys that were strangers split, 5 girls that were friends stole while 1 girl split, and 3 girls that were strangers split while 2 stole.
Okay, so for our final results, we decided to check between boys and girls and strangers versus friends. For boys versus girls, we determined that girls were more eager to split, and for strangers versus friends, we realized that strangers were more eager to split.
Alright, so we wanted to further explore the topic, so we went on YouTube and watched big content creators like Mr. Beast, who had more to give, so we wanted to see if the results for boys versus girls would still match up if the stakes were higher. And for boys that split, 12 split while 13 stole, and for the girls, 17 split while 16 stole. So, as you can see, the data said that boys were still more likely to steal with 52% stealing and 48% splitting, and the girls were still more likely to split with 52% splitting and 48% stealing, further proving our hypothesis.
In conclusion, the results of our experiment align with our hypothesis that males would be more likely to steal than females, but disprove our hypothesis that strangers would be more likely to steal than friends. This experiment was a great display of how the prisoner's dilemma would be determined between females and males and their relationships and how that would affect their decisions to split or steal. Although we only had a small sample group when compared with other examples of the experiment being conducted, our hypothesis, when based on gender, still proved to be true even at higher stakes.
All right, does anybody have any questions? Yes.
For the data about So I went on YouTube and I was just watching, definitely spent 2 hours just straight watching YouTube videos and recording the results of these. And so it's 15 or 25 for the boys and then 33 for the girls. So, yeah. What's
Why
up?
don't y'all choose this topic?
Well, I'm not gonna lie, my answer to this, they gave us a big long list of about 20 math topics, and I really didn't know what any of them meant. And so, prisoner's dilemma sounded something on the crime side of things, and I thought that sounded really cool. And so this is what I picked, this is what I made it up. What's up, Miles?
What was your hypothesis that boys would steal more than girls?
Not to be controversial, but it kind of just seems like, I mean, we all came to that same agreement, so it was a 5v0. Anybody else? You in the back.
Did y'all do this experiment on yourselves? And if so, which did y'all choose?
We did not do the experiment ourselves.
Which one did you choose?
Depends on who I'm against.
I'm stealing every time.
Alright, we're gonna get started with our next group. So this group is gonna be talking about non-Euclidean geometry.
Welcome. I hope you're all doing well, and thank you for joining us tonight. My name is Paola Jaime Martinez.
My name is Edgar Cirilo Tranquilino.
And my name is Mika Gard. Today we'll be presenting one of the most fascinating sections of math, which is non-Euclidean geometry. We will start off with a brief overview as to why non-Euclidean geometry came to be, followed by an introduction to the basics. Then we have a fun little bit with an audience member. And then finally we'll finish off with a slide of other applications that non-Euclidean geometry is used in the real world. So our story begins in 300 BC. Euclid of Alexandria compiled the Elements, a compilation of 13 books that talked about mathematics and geometry known at the time. So in those 13 books, they went over postulates, which is an accepted concept that is taken as a basic principle. It is also called an axiom. And proofs, which is evidence and or logic used to prove an idea or a statement. Okay, and Euclid used these to build up mathematics from the ground up. He essentially wanted to create a big mathematics books that mathematicians, physicists, and biologists would look back to for thousands of years. And eventually, Euclid came to conclude 5 of his own postulates, which we still use for modern geometry. And they are as follows.
Alright, so the first postulate we have is that a straight line segment can be joined by any 2 points. The second one we have is that any straight line can be extended indefinitely in a straight line. The third one is, given any straight line segment, a circle can be drawn having the segments as radius and 1 point as the center. The fourth postulate is all right angles are congruent. Now, the fifth one, and the longest one, if 2 lines are drawn that intersect a third in such a way that the sum of the inner angles on one side is less than 2 right angles, then the 2 lines inevitably must intersect each other on that side if extended far enough. Now, if you have a line, a straight line, and you have another straight line and bent at an angle, those 2 lines will eventually meet up. This is known as the parallel postulate. Now, the big problem is, what about the 5th postulate stands out to you most? It's big. It's very big.
Yeah, it's really long.
It's really long. So, Paolo will explain to us what's the problem with it.
All right, Eric, as you pointed out, it's very long and very wordy. So, like to you and to other members of the audience, mathematicians were really bothered by this. And when they tried to prove the 5th postulate using the other 4, they just couldn't. It was just too awkward and unnatural to them. So they began the search to eliminate the 5th postulate, because you know what? We have the other 4, maybe we can derive the 5th. All right, but they couldn't do it, right?
So it wouldn't be until the 1800s when some of the greatest minds to ever exist would actually bring forth a simple idea. Generals Boyar, Nikolai Lobachevsky, and Karl Friedrich Gauss, independently of each other, brought forth the idea that the fifth postulate can only be assumed and proven false in a dimension, world, or plane that was not flat, meaning that this space had to be curved. No matter what you did, you could only draw a curved line. Right, so remember the fifth postulate dealt with parallel lines, and on a flat plane, lines are straight and never meet if parallel. However, if the plane is curved, parallel lines can eventually meet. So within the late to mid-1800s, Carl Friedrich Gauss coined the term non-Euclidean geometry to refer to this type of geometry. But today we now know it as a subset of non-Euclidean geometry, which is called spherical geometry. More on that later. But today, non-Euclidean geometry is an umbrella term for any type of geometry in which the fifth postulate doesn't hold and is replaced by something else. But the first four are still true, and the two main types are spherical and hyperbolic. In these dimensions, spaces, the world is wacky, abstract, and even weird. Mathematically, the math is still logical and sound, so there's nothing we can really do about it. In this presentation, you will be submerged into a different dimension where our understanding of our own universe breaks and another begins.
So that brings us into our next question. So is the shortest path always straight? We can use the Pythagorean theorem to help us answer this question. The Pythagorean theorem is a squared plus b squared equals c squared, and we use it to solve for the length of the sides of a triangle, where a and b are the legs and c is the hypotenuse. One of the things that this theorem proves is that c must be shorter than a plus b. That means that the shortest path between 2 points on a flat plane is this straight diagonal line. Keeping this in mind, let's discuss Hilbert's axioms. These are another set of geometric rules that are very similar to Euclid's that are seen as the foundation of geometry. These rules are applied to both Euclidean and non-Euclidean models. For standard Euclidean planes, the axioms are applied as usual because of their similarity to Euclid's. For non-Euclidean planes, since they don't use Euclid's fifth axiom, this axiom must be replaced with another, which is typically one of Hilbert's. So what are these alternate axioms? First, let's break down Euclid's fifth axiom into Playfair's axiom. This statement simply restates Euclid's fifth in a more concise, understandable way as, through a point not on a given line, there is exactly one line parallel to the given line. Next, let's look at our alternate definitions. Hyperbolic geometry follows the principle that the angles of a triangle add up to less than 180 degrees, and infinitely many lines can be parallel. While elliptical or spherical geometry follows the rule that the angles of a triangle must add up to more than 180 degrees, and parallel lines cannot be drawn. In order to understand this, we first have to clarify the definition of parallel. So when we call a line parallel to another line, we mean that these two lines exist in the same plane and will never intersect. In hyperbolic models, infinitely many lines can be drawn that will never intersect, while in elliptical and spherical geometry, any line we draw will intersect at some point. Taking a look at this diagram, we can see how a flat triangle drawn in Euclidean space will differ in these two geometric models. The most noticeable difference is the angles. The elliptic model's triangle has an angle sum greater than our normal triangle, and the hyperbolic model's triangle has an angle sum less than our normal triangle. You can see how the elliptic triangle seems to curve out because elliptic models have positive curvature. Contrastingly, the hyperbolic model's triangle seems to curve inwards because hyperbolic models have negative curvature. So, why do non-Euclidean models work if they seemingly break our rules of geometry? The answer is because of its relative consistency. This form of geometry works because it's consistent with Euclidean space. If something works in Euclidean space, it will work in non-Euclidean space, and if it doesn't work in Euclidean space, it also will not work in non-Euclidean space. If we take a look at this diagram, we see that these two models can be projected into Euclidean space and vice versa. The upper half plane model is one of our hyperbolic projections. This plane is the upper half of the complex plane. We also have our Poincare disk model, which is also a projection of hyperbolic geometry, except presented as a disk. The inside of the circle is used to represent the space of our hyperbolic model, and the lines are represented by the arcs and diameters you can see within the disk. We use stereographic projection to do this, which is simply mapping the points from our non-Euclidean model to a plane that exists in Euclidean space. Each non-Euclidean line is translated into circles or lines that are Euclidean. We use this method of projection because it helps us preserve the angles of our original model and helps us better visualize hyperbolic models on a flat plane.
Alright, so for this section of our presentation, we're going to ask for one volunteer to come up. I saw your hand first. Alright, so on this globe we have here, I need you to draw the shortest, what you think the shortest path from LA to London is. Would you like to show the audience? All right, thank you. All right, this is actually the shortest path. You may be asking, what? As we all know, the Earth isn't flat. It's a sphere. When planes fly straight, they're actually following a curve called a great circle. A great circle is just the shortest distance between 2 points on a sphere. Since normal geometry assumes flat surfaces, we can't really use those straight line rules in non-Euclidean geometry. Instead, we use spherical geometry, which gives us this formula. This equation helps us calculate the shortest distance around the Earth's surface. It uses the latitudes and longitudes to be able to, of the 2 points and the Earth's radius. The distance d on the equation is what airplanes use to follow the route in order to save fuel and time. So even though it looks curved on a flat map, the curve is a true straight line in spherical geometry. Now, like I said before, a great circle is the shortest path between 2 points on a circle. Even though it looks curved on a flat map, it's actually the straightest line possible when you're traveling across the globe. A geodesic is just a fancy word for the shortest path between 2 points on any curved surface. If you're walking on a mountain range, for example, the geodesic path is the one that cuts across the terrain as efficiently as possible, even if it zigzags. So what's the difference between a great circle and a geodesic? A great circle is a type of geodesic, but it only works on spheres like Earth. Geodesics can exist on any type of weird shape, whether it's a sphere or, for example, a Pringle chip. That is a form of hyperbolic geometry. That is why planes fly along great circles. They're following the geodesic path on a sphere in order to save time, distance, and fuel.
And then these are just some more examples of curved flight paths. In the second example, you can see how the great circle path compares to the straight line path. Okay, and then some other applications for this concept. So first of all, we have accurate navigation. The Earth is a curved surface, as we stated before, so using spherical geometry gives us more accurate flight, ship, and GPS routes. Without it, our straight lines would be incorrect, which would result in longer travel times, fuel waste, or even navigation errors. It's also used in GPS and phones. So GPS satellites orbit Earth and use spherical geometry and relativity to pinpoint your exact location. Apps like Google Maps rely on this math to guide you to your location turn by turn. It's built into our everyday routines. It can also be used in air travel because airlines save fuel and time by flying across these great circles rather than flat lines. Every plane ticket price and flight time depends on this math being right. And lastly, it's used in ocean shipping because ships also must follow the curved paths to reduce distance, which affects trade, delivery times, and the cost of any goods that you buy. And then these are citations. So does anybody have any questions? Yes.
Why did y'all choose this topic?
Okay, so the question was, why did we choose this topic? So
We all willingly chose this topic without like knowing who we were going to be with. So I chose this topic because I didn't know what it was. So I wanted to investigate and just learn more than what I already know.
I originally chose electromagneticity. We didn't get that, but I chose this as my second option because I like to do topology, and I was like, geometry is a part of topology, and I found that really interesting, so I put this down.
And I chose this topic because I've always enjoyed geometry in school, so I thought this would be an interesting way to learn more about a new section of geometry. Any other questions? Yes.
Are there any, if you were to like continue this research, what like area would you like to focus in on more that you find interesting while you're researching?
Okay, so the question was, if we were to continue researching, what area would we focus on next time?
If it had to be different than navigation, we probably would have done space-time. That's a very interesting subject because up to this point, we don't really know what shape our universe is, so that would be an interesting thing to introduce to you guys. If we were to continue on navigation, we would like to make our own research and see how much time it would take a boat or plane to get to its destination using manual calculations.
All right, we'll have one more question if anyone has one. Yes.
Okay, this might be a stupid question, but basically, if I were to walk directly to you, that straight line would be the shortest path in Euclidean geometry. But if for non-Euclidean, would it be slightly curved, or are we like very zoomed in into the Earth that we're not really seeing much of that curvature, therefore we don't need to use non-Euclidean geometry to go for that?
Okay. Everybody heard that, I'm assuming. So her question was, if you were to walk to me, would we have to necessarily use non-Euclidean geometry? No, because we already said that in the Pythagorean theorem. So where we use this whole entire area, that is when we're going to have to use some form of non-Euclidean geometry, aka the equation I gave off. But for flat planes, we'll just have to use the Pythagorean theorem for now. So, anyways, this is our presentation, and we want to thank Sarah Ruth for helping us on our way and helping us learn a lot of heavy topics on this. So we want to thank you. And yes, thank you.
Hello everyone. So this is our presentation about tessellations. This is the crew. I'm Aubrey.
Zoe, Lily,
Roderick.
So for reference, a tessellation is a collection of shapes that fit together without any gaps or overlaps and continues to infinity. As we say in the slide, where no gaps are left and knowledge is unknown. Today we'll be diving into the world of tessellations. Here's what we'll cover. First, we'll look at the types of tessellations, regular, semi-regular, and non-regular, as well as how they differ from one another. Then we'll go through a step-by-step process for how tessellations are built. After that, we'll explore some inspired artists, like M.C. Escher, who turned tessellations into works of art. Next, we'll look into the history of tessellations and how they've appeared in different cultures and time periods. And finally, we'll talk about how to create our own tessellations, with examples and ideas to try ourselves online. Let's get started.
So, a regular tessellation is made by using only one shape over and over again to fill in the space of the plane. There cannot be any diversity in shapes, which means that they can only be one shape, like a squares, triangles, pentagons, whatever. There are only three types of regular tessellations, which are triangles, hexagons, and squares. And there are only two, and these are the only types of regular tessellations due to how the angles are divided throughout the shape. So at this vertex, The angle here is 120, which divides into 360 3 times, which explains why there can only be 3 at one vertex. If you look at the pentagon has 108 degrees at a vertex, so it cannot divide evenly 360, so which makes it have a gap in the tessellation.
So a semi-regular tessellation is a tessellation that is made with 2 or more polygons. There are 2 properties of semi-regular tessellations. The first is that it's formed by regular polygons, and the second that the arrangement of polygons at every vertex point is identical. So part of semi-regularity is that there are 8 variants that exist, but we will discuss this more in the next slide. Some examples of semi-regular tessellations are composed of triangles, squares, and hexagons. These polygons are used to create the negative space and leave no gaps. As shown in the photo on the screen, they can use shapes like octagons and hexagons to create the tessellation. The decagons are also another polygon that are used to create semi-regular tessellations. And so since we left you on a cliffhanger, here are the 8 variants.
There are 8 variants of semi-regular tessellations, and they are sorted by their vertex identifications. So in order to label the different types is you take a vertex and you go around identifying the shape and how many sides it has. So if you come over here and you go down here and you pick this vertex, you'll see that there's a square, and then you have an octagon, and then another octagon. So then the vertex identification would be for 8, 8. And so the limit of 8 arises from the fact that at a particular vertex, the summation of the angles must add up to 360 degrees. And so these are the only combinations of regular polygons that work.
A tessellation is just a pattern where shapes fit together with no gaps and no overlaps. While regular tessellations use repeating shapes like squares or triangles, non-regular tessellations can be made from any shape, even ones you completely make up as long as they repeat across the plane. These shapes can have all kinds of edges, curves, and borders, and they still work, as long as they fit together in a non-repeating way. A fun example is the penrose tessellation, such as this example on the slide. It is made up of shapes that fit perfectly together, but they don't repeat in a regular pattern. That makes it aperiodic. You can keep extending it forever, and it will never form a predictable pattern. Even simple examples, like the brick wall pattern, count as non-regular, because the rectangles are staggered, not lined up evenly. Non-regular tessellations are a mix of art and math, and a great way to show how structure can still come from unpredictable and unusual shapes.
So, the picture on the right is a design that you can see at a local restaurant or home. It's a pretty normal tessellation and pretty much the average tiling. And on the left is a picture of a tessellation that can be found on the ceiling of the tomb of Jabez in, I'm pretty sure, Israel. On the left is a ballarat pattern, and it is a culturally Italian tessellation. And on the right is a design that can be found in Northern African tradition, and it is a non-regular tessellation.
Now that we understand what tessellations are, we'll go over how to make one by hand, just so we know the basics before we move on to making one online. First, we'll start with a piece of paper, a pencil, and a pencil. Super simple materials. Then we'll divide the paper into equal width rows, about 3 to 4 rows total. In one row, we'll draw a simple shape, like a square, triangle, or circle, and repeat it side by side. After that, we'll copy the same shape into the row, so the entire page fills up with the design. Once that's done, we'll color it in to bring the tessellation to life, and it's ready to be displayed. This is a physical version of making a tessellation, but after we go through the inspired artists, we'll be creating our own tessellations online, using the same idea but with digital tools.
One of the artists most inspired by tessellations is N.C. Escher, who is commonly influenced by mathematics, with different aspects of it appearing in all of his art. He studied architecture and then switched to studying graphic design. While he is famous for impossible drawings, his work with tessellations is influential in the field. He became inspired by the Moors at the Alhambra Palace in Spain, where this bottom tessellation comes from. And then, in order to create his own tessellations, he would sketch a grid, and then he would manipulate the shape to create all sorts of animals, such as fish, lizards, and birds. Robert Fowler's work is largely based on mathematics, and he also takes inspiration from M.C. Escher. He received a bachelor's degree from the University of Denver, double majoring in physics and mathematics. He works to combine math and art in his creations and make both accessible through his puzzles, which can be solved in a variety of ways, as seen in the first image. And he founded this business in 1993. He also combined tessellations with fractals, as seen with the dragons, expanding the horizon of tessellation use. While his work isn't limited to this field, that is a topic for another day.
So the earliest recorded examples of tessellations date back to ancient civilizations in Mesopotamia and Egypt. Early examples of tessellations were for adorning buildings, pottery, and other artifacts, and also include some architectural designs. In Mesopotamia, around 4000 BCE, the Sumerians used tessellations to create intricate patterns on their pottery and in architectural designs. In Egypt, around 2500 BCE, tessellations were used to decorate tombs and other structures. Islamic art and architecture are renowned for their extensive use of tessellations. They used tessellation to adorn mosaics, palaces, and other buildings, and mainly occurred during the Islamic Golden Age. In addition, the ancient Greeks and Romans used tessellations in their art and architecture. The mosaics often depicted mythological scenes to decorate the floors and walls. Overall, the uses of tessellations date back as far as 4000 BCE and has been used over the years to decorate buildings and to create intricate designs that is appealing to the eye. So on the right is a picture of a tessellation that is Patio de los Leones in the Alhambra. This is an example of thinner's grid architecture. And this was a decorative scheme that is very eye-catching and very appealing to the eyes that people love to walk through. It is absolutely gorgeous and part of architectural tessellations. And the one on the left, an example of a tessellation art. So this is a picture that came from an article that actually talks about the different types of tessellation art, but also the beauty of it. It was written by Isabella Meyer. And these are our citations. Thank you. Are there any questions before we move on to our interactive part? No? Okay.
This is a QR code you can scan that allows you to create your own tessellations, allows you to play with it. You can make it 3D, you can make it 2D, you can rotate it. You can do a lot of things with it. So if you click on it, you can just start trying to make your own.
I'll give you guys a few minutes to log in, and then we'll switch over to a slide with a couple of challenges for you guys to recreate tessellations. Your challenge is to replicate them using the website. Take your time, pick a design, and see how closely you can match it. We'll be walking around if you guys have any questions or concerns. Thank you for participating and have fun tessellating.
Hello everyone, my name is Willie. My name is Jason. And we will be presenting our mathematical investigation on sleep and its impact on health. Before we begin, I'd like to ask a simple question. What can sleep duration affect? By a show of hands, who thinks A, brain size? Okay, who thinks B, blood type? No. Who thinks C, bone density? And who thinks D, blood pressure? Alright, well, it seems like most people chose D, blood pressure, which is correct. As we know, sleep is essential for many bodily functions. However, sleep disorders are becoming increasingly prevalent globally, and many people are not receiving enough sleep. So insufficient sleep is believed to contribute to the development of high blood pressure or hypertension, which can lead to serious health complications. The constant pressure from hypertension can accelerate plaque buildup and damage blood vessels, which can lead to increased risk of chronic kidney disease, strokes, or heart conditions. This is particularly concerning as it implies that many people around the world are unknowingly putting their health at risk due to inadequate sleep.
When we were researching this issue, a question immediately came to mind. How can we really be sure that there is a link between sleep duration and blood pressure? To explore this question, we turn to linear regression. It It is a statistical method that can help identify patterns and relationships. To briefly explain how linear regression works, the first step is to collect and clean data. We use a dataset compiled from Oxford University that included the sleep duration and blood pressures of random individuals. We cut down the data to only include people from ages 30 to 45. We found that this was the best way to minimize the impact of age-related factors on blood pressure while still preserving the dataset's integrity. The next step is to find the line of best fit. The phrase best fit refers to the line that best represents the general trend of the data. So if you were to plot the data points on a graph, the line of best fit is a straight line that comes as close to as many of those points as possible. Once we have this line, we can then use it to make predictions about the relationship between the two variables. We'll discuss this more later. Instead of simply eyeballing the line of best fit, there is a precise mathematical method you can use to calculate it. However, since our data set contained over 200 elements, doing it by hand would take a really long time. Instead, we wrote a Python program to do the calculations for us in the fraction of the time. During this walkthrough of our program, we'll include snippets of our code that correspond to each step that we discussed. First, the code sets the parameters, the slope and y-intercept to 0 as a starting point. These values will be continuously adjusted until they are able to produce the line of best fit.
So let's talk about the line of best fit again. Earlier we said it is the line closest to as many of the data points as possible. But how can we measure just how close the line is to those data points? One way is by using mean squared error, or MSE, a method of evaluating the quality of the line of best fit. To start with, our code uses the slope and y-intercept to calculate predicted values. Next, we subtract the predicted values from the actual values to get what is called a residual. For example, if the predicted value is 5 and the actual value is 9, then the residual would be 4. Next, we square all the residuals in order to ensure that we're only working with positive values so that the residuals don't cancel out. For example, if we have a residual of 5 and a residual of -3, if we simply added those two numbers, we would get a combined error of 2, when instead we would want the error to add up over time for each residual. And finally, we add up all the squared residuals and divide by the total number of data points.
Now that we have a way to measure how well our line fits the data, the next step is to actually find that line. Our code uses gradient descent, an algorithm that adjusts the slope and y-intercept values until the optimal line is found. First, imagine the loss function, in this case, the mean squared error, as a surface in 3D space. As seen in this image, you can think of it as a hilly terrain. The height of the surface at any point represents the amount of error at that point. The goal is to navigate to the lowest point on the surface to minimize the error, just like trying to find the lowest point of the valley. To do this, we find the partial derivatives, which measure how much the error changes when either the slope or y-intercept change. So suppose you are standing on a hill. You can either walk left and right or forwards and backwards. The partial derivatives would measure how the height of the hill changes when you walk in one of these directions. When you combine the two partial derivatives, you get the gradient vector. An important property of the gradient vector is that it always points in the direction of steepest ascent. So going back to the hill analogy, you can think of the gradient vector as a path that shows you the fastest way to climb up the hill. However, since we want to decrease our error, we actually have to go in the opposite direction the gradient vector is pointing. To do this, we first multiply the partial derivatives by a number called the learning rate, and then subtract that product from the slope and y-intercept values. The learning rate is a number that determines the size of each update. So if the learning rate is too big, then the code might overshoot the correct solution. And if it's too small, the process would take a really long time. So the code repeats this process until the error stops changing by a very small number, which we set to 0.000001. Here's a clip of the code that we wrote. So as the code runs, you can see on the right that the error is gradually decreasing, and the code eventually stopped at 39,235 iterations. So what that means is the code went through the entire process we just described 39,000 times to find the best value. So you can see how we really had to do this in code, that it's not practical to do by hand.
Okay, now that we've describe how we achieved our line of best fit, we want to pose a challenge for you. Can you beat our code, or can you draw a line that has an error lower than our calculated error? And if you win, you'll get some money. Does anyone want to volunteer? Great shirt.
Yeah.
What's your name?
My name is Ray.
Alright, so what you're gonna try to do is draw the line of best fit, or make the line match as many of the data points as possible. And to do that, you're gonna use these two sliders. With this one, you can adjust the angle of the line, and with that one, you can move the line up or down. And when you finalize your line, just like
Is that good, guys? Tilted?
Flip the slope. Opposite slope.
move it around. I want out.
The slope is decreasing, not increasing. The slope is decreasing. Inverted.
Alright. Does anyone think they can beat this line? Alright, so now I'm gonna reveal what the error is. Now I'm gonna reveal what the error of your line is. So your line had an error of 75.487. Does anyone think they can get an error lower than that?
Now you got it.
Robert.
Yeah. No way. There should be a yeah. There. Should be a little more. I don't know. What do you think?
Alright, so you had an error of 43. We'll take one more person and try to get an error. You.
So he's saying that's
43. our calculated line is. Okay, so our calculated line is the green line, as you can see. The equation for it is y equals negative 3.334x plus 149.427, and our calculated error is 35.864. So unfortunately, none of you guys beat our error, so no one wins any Alright, so now that we've seen that there is a link between sleep and blood pressure in our samples, we have to see how significant those results really are. And the way that we're going to do that is through a hypothesis test. So imagine you had a coin and you wanted to see if the coin was fair. So you flipped it 100 times and you got 60 heads. Is 60 heads enough evidence to prove that the coin isn't fair, or was it simply a coincidence? A hypothesis test lets you take the results, do some math, and figure out, are the results surprising enough to reject the idea that the coin is fair? So the first step of a hypothesis test is to identify your hypotheses, the null and the alternative hypothesis. The idea of the null hypothesis is that there hasn't been a change or there is no effect. So in our case, there is no relationship between sleep and blood pressure. The idea of the alternative hypothesis is that there has been a change or there is some effect. So in our case, there is a relationship between sleep and blood pressure. Now imagine it as a courtroom. The null hypothesis says that a person is innocent, while the alternative hypothesis says that a person is guilty. The only way to conclude that the person is guilty is by finding strong enough evidence to prove so, thus rejecting the null hypothesis. We also have alpha, which is called the significance level, that we set to 0.01, and we will use this value to compare to the p-value, which I'll explain later on. So this is our formula for the linear regression t-test. The lowercase b is the sample slope, it is the slope of our data set. The capital B is the population slope, it is the slope of the population from which the sample was taken. S of b is the standard deviation of the residuals, and t is the test statistic, which tells us how far we are from the null hypothesis. So when we plug in our values, we get t equals negative 3.3 minus 0 over negative 0.634, and our final answer, we get 5.2041. Now that we have our test statistic, we have to take it one step further and find what is called the p-value. The p-value is the probability that, assuming that the null hypothesis is true, or that there is no relationship between sleep and blood pressure, is the probability of finding a sample exactly like ours with a slope of negative 3.3. So how do we calculate the p-value? We use what is called a t-distribution table. And so as you can see on the table, the dotted blue lines, which is this, is our critical value. And the area outside of those critical values are what's called the rejection region. If our test statistic falls in the rejection region, we can conclude that our results are statistically significant. So as you can see on the table, the dotted purple line, which represents our test statistic, is outside the dotted blue lines, meaning that our results are significant. But to actually calculate the p-value, we have to use something called the t-CDF function. The t-CDF function calculates the area outside of the critical regions under the curve, and we have to multiply that by 2 to get both rejection regions. And when we do that, we get a final number of 4.15 times 10 to the negative 7. So this is an extremely small number, and what it means is that it's essentially impossible to get a sample like ours if there is no relationship between sleep and blood pressure. So therefore, it's much safer to conclude that sleep and blood pressure are linked. So because the p-value is less than our significance level, 0.01, our results are statistically significant, meaning we can use our results to say that less sleep leads to higher blood pressure. Thank you for listening.
Good evening, everyone. Today we'll be exploring the Collatz conjecture. My name is Zaina Khan.
I'm Charlotte Pasco.
I'm Andrew Hewell.
And I'm Hershini Beluso.
So imagine you have a number, like pick any number. If it's even, divide it by 2. If it's odd, multiply it by 3, then add 1. According to the Collatz conjecture, if you repeat this process enough times, reapplying those 2 sets of statements to the new result you get, if you repeat it enough times, no matter what number you start with, you will eventually end up in a loop between 4, 2, and 1. However, it may not be true for all numbers. It's possible there could be very high exceptions. So let's walk through an example of what this whole divide by 2, multiply by 3, and add 1 would look like. Take the number 26, for example. So 26 is even, so we're going to divide it by 2, which gives us 13. Now 13 is odd, so we multiply this by 3 and add 1, which gives us 39 plus 1 is 40. 40 is clearly even, so we divide by 2, giving 20. 20 is even, so we divide by 2 again, giving 10. 10 is even, so we divide by 2 and get 5. Now 5 is odd, so we're going to switch back to doing multiply plus 3, add 1, which gives 15 plus 1, which is 16. 16 is even, you divide by 2 and get 8. 8 is even, you divide by 2 and get 4. Now this is the critical point where we've reached the 4, 2, 1 loop. Because you can see 4 is even, you divide by 2 and you get 2. You divide by 2 again and you get 1. 1 times 3 plus 1 is 4. Because it's odd, so we're just going to get right back to 4 again. And you can see that even though we started with 26, we ended up in this 4, 2, 1 loop. And it is hypothesized that no matter what number you start with, you will always eventually reach this 4, 2, 1 loop.
So I'm going to talk to you guys a little bit about the history of the Collatz conjecture and what it really means. So Collatz was a German mathematician who proposed this conjecture in 1937. And a conjecture basically means that it's a conclusion, but it's not based on complete information. So he's theorized that this is true, and he can test it up to quite high numbers, but he can't prove that it's true for all of the numbers that there are. And this is demonstrated. You can see the paths in that graph over there, that up to 1 million, they still flow back down to 1, and you can see basically every number there is just converging back down to 1. And over history, many other mathematicians have studied his conjecture and tried to find proofs for it, but there has not been a definitive one found yet.
Okay, so moving on to the proof techniques, obviously the Collatz conjecture has been around for a while, and we've tried different things to help prove it. So to begin with, the computational method basically uses like any electronic device, so computers, calculators, and that stuff, to just like show that any number you plug in leads to the Collatz conjecture. Furthermore, this has also allowed for like different developments to be made in like industrial tests.
Another attempt to prove the Collatz conjecture is the induction method, which is a method that we learned here at Governor School. So in base 10, we're able to prove the first step of induction. However, whenever we try and do the second step of induction, we cannot prove it. Many mathematicians theorize that it's impossible to do. So what some mathematicians have done is use a binary representation of both the Collatz conjecture and induction in order to prove the second step. However, no one has found a way to prove the first step in binary.
Another method that's been attempted to prove the Collatz conjecture is functional analysis, which is kind of studying topological space and vectors in there and analyzing how the Collatz conjecture function maps out within that space and what sort of loops there might be other than 4, 2, 1, and what sort of characteristics numbers that did not converge to 4, 2, 1 would have to have.
And the final method we looked at, and my personal favorite, is called clustering. And basically it shows patterns in the numbers that we have tested. So we've tested the Collatz conjecture all the way up to 2 to the 68, which is huge. And what we can do is we can represent on a graph like this one shown there. And as you can see, there's sort of lines and patterns and convergences. And by studying those convergences, mathematicians theorized that they could find patterns that could give a solution, as if it always follows the same pattern, that would give us a y and a how to the way it works. Okay, so now it's time for our interactive component. So, just a second while we pull up the thing. Okay, so can anyone volunteer to give us a number, maybe 2 digits? There.
47.
47? Okay, so
we'll input it here and press start, and this little rocket with a number on it, if the number is even, it'll go to the divide by 2 rule. If it's odd, it will go to the 3x plus 1 rule. And on the left, you can see the graph with different iterations as the values go up and down as it goes through the process. And
basically, as this graph shows it, you'll start to see spikes and it'll start going down. And essentially, as the graph goes on, it'll eventually end up in a loop at the bottom that we'll get to eventually. But it'll peak at some point, and the graph tends to drop off pretty dramatically after it peaks. But it's very inconsistent. Some numbers go down really fast, and some numbers right next to it, like 26 collapses almost instantly, and 27 goes all the way up to 9,000. Don't pick that one. We aren't sitting here for that long. So basically, that means that it's really hard to prove. That makes it even harder to prove because these two numbers that are one away have completely different results when you go through the theorem. So that makes it more difficult to, yeah.
And what we were talking about before with like a dramatic collapse down kind of scene here is that if you think about it, multiplying by 3 is going to increase more dramatically than dividing by 2 will. So in order for the number to eventually converge down to 1 and not increase exponentially forever, you have to divide by 2 multiple times in a row and have a number where you can just, it's even, and you divide by 2 and it's still even, still even, still even, so that you can collapse down and not convert and not just diverge to infinity.
And as you can see, even with a number like 47, we've gotten all the way up to like around 5,000, or I guess 7,000 now.
The sevens. It's always the sevens.
Yeah, it's always the sevens. They take forever.
Which, if you think about it, this is why it's so hard to prove computationally. First of all, you can never prove it computationally because there's going to be another number. You can only disprove it computationally. But also, if this is the amount of time it takes to prove one small number, and having to run all these iterations for like numbers that are like billions of digits long takes forever. But there's been a pretty dramatic drop off there, you can see.
And as we get close to the end, eventually we'll hit a number that it'll start to converge at. And on the graph I showed earlier on the early slide, you can see sort of choke points where a lot of numbers would converge into 1, such as like 40 is a pretty common one, as well as 16. And once it hits those really even numbers, it starts to converge really rapidly, and you'll notice a pattern.
Yeah, so I think we're almost getting to that 40 point. It's a little bit squished since we got to such high numbers, but over there it starts in a repeating sequence, which is representative of the loop. So, does anybody want to try a different number just to see? No more 77.
97.
67.
56.
56. Okay.
57.
Okay, let's try 56. Yeah.
One thing is, like we were talking about the choke points before, if you do this a lot, you know certain numbers that collapse, which is some way you can like eliminate it, because if you get down to a number that you've already proven that will go down to 1, then like you don't need to prove it. Say like a lot of numbers go through 844, a lot of really high numbers. So if you're like, oh, I got to 844, I don't need to prove that anymore. Hopefully this doesn't go to 844.
Yeah, so we're back in it, and now you can see on this graph a little bit clearer how it looks. It will just keep going in that 4-2-1 direction. But, you know, like 56 and, what was the first number? 47. They're not too far apart, right? Like less than 10 apart, but they have vastly different iteration times, and that's what makes this so difficult to prove, because there's not really anything analogous about how it affects different types of numbers. Okay. Does anybody like really want to try another number?
256.
2 digits, please.
13.
99. 99 is out.
Okay, yeah.
Have you tried it with any large numbers, like over a million?
We've tried it up to 4 digits.
The thing
Yeah.
is, like, I sometimes, you can do this on your own with a calculator. The issue is if you get to really high numbers, the actual computations take longer, and really long, like calculators will stop showing you the digits and they'll put it in scientific notation, which is hard for telling if it's even or odd.
Yes, and also the thing about this algorithm is it's kind of in that game format, so with the rocket moving, it takes a little bit faster than it would to just have it go through in a program. So using this for really large numbers would take quite a while, but even like a 4-digit number, odd 4-digit number, took only around like a minute and a half-ish, so it just depends, yeah.
But if you do this using a calculator by yourself typing in, you will beat this program. We tested it.
Yeah, we tested it. Charlotte did it with a calculator at the same time as a program, and it went a little faster, but I think that might be because of the animation.
And then the other thing is, like, our program could take longer, but there's really large supercomputers that are basically dedicated to doing this, but without a rocket, so.
That's how they got to 2 to the 68.
Yeah, and even if you are able to compute those really high numbers quicker, it doesn't necessarily mean that that's like going towards proving the conjecture, just because there's infinitely many numbers, so we'll have to prove it infinitely. So finding a general case or those methods that they discuss, like functional analysis, those like pattern techniques are going to be important in trying to prove this. Okay, so we'll continue with the presentation.
Alright, so as we were kind of talking about as the game was going on, no general proof really exists, and many mathematicians speculated that if a proof did exist, it would have to be infinitely many lines long. As well as with the game, we were limited in our computational powers. We were only able to test numbers up to 2 to the 68, which can take millions of iterations to get down to 4-2-1 loop. And also the unpredictability of it makes it so complex, because numbers like 26 will collapse in 5 iterations, and 27 will go all the way up to 9,000 before finally collapsing.
So the implications show us why the coalesced conjecture is important to study. So to begin with, it'll help with advancing fields, especially that have to do with abstraction. And abstraction is like basically like derived from like randomness. So like for the coalesced conjecture, when you're trying to prove it, like we just showed you in the game, we plugged in a lot of random numbers, and then at the end of the day, it went down in that 4-2-1 pattern. So furthermore, it also acts as a benchmark to show where we lie with computing efficiency and how fast we can do it. We talked about supercomputers, and at the same time we also have our games, so that shows you that difference. And lastly, it'll also lead to breakthroughs with other mathematical proofs and stuff in number theory, dynamical systems, and more. So for example, Fermat's last theorem, commonly known to like not be able to be solved for centuries, and once it was solved, like around the 90s, it also led to other discoveries in terms of other math proofs.
Are there any questions? Okay, thank you so much, everyone.
Thank you for being here. We will be presenting the Golden Mean Shaping Art from the Golden Ratio, which is our GSC 2025 Math Cornerstone. But before I tell you what the Golden Ratio is, I want to ask you a question. So on the screen, there are 4 rectangles, and the fourth one is a rectangle. It's not a square. Now, I want you to think to yourself which one you think looks like the most perfect standard representation of a rectangle. If you guessed 3, you are right. And the reason is because it is actually known as the golden ratio. So the ratio of its length to its width is equal, the golden rectangle is equal to the golden ratio, which is this irrational number. The exact number of the golden ratio is 1 plus the square root of 5 over 2, and it is represented in math by the Greek letter phi. Now, if you take the length and the width of the golden rectangle and you put it in a straight line, we can label the short part A and the long part B. Now, the length of the total width of the line over the long part is actually equal to, or the ratio is equal to the ratio of the long part over the short part. And it is also equal to the golden ratio, or phi. Now, if you split up the fraction, you can also see that it is 1 plus the short part over the long part, which is equal to the long part over the short part, the ratios. Okay, now if you have heard of the golden ratio, you're probably familiar with the golden spiral. And how you create that spiral is by taking the golden rectangle and then putting a square inside it, and that will create another golden rectangle. And then you put a square inside that golden rectangle and a square inside that golden rectangle. And then you just do that over and over again, and you can draw a spiral between the vertexes of the squares. So it looks like this. Now, this spiral can be found in many places in nature, including your ear and ocean waves, and also your face. This is very closely aligned with the Fibonacci sequence, the golden ratio. The Fibonacci sequence is a sequence of numbers where you take 0 and 1, and then you add the last two numbers. 0 plus 1 is 1, and then 1 plus 1 is 2, 1 plus 2 is 3, and so on. So eventually, you can take the ratios of these numbers, and it will get very close to the golden ratio as you go further down the sequence. Now, here's Rama with a little bit of history behind the golden ratio.
Okay, so there is no known history date to the discovery of the golden ratio. However, the very first official mention to it was in Euclid's books that called Elements that he wrote back around 300 BC. However, it wasn't called the golden ratio, it was called the extreme and mean ratio. It wasn't called the golden ratio until around the 1800s. So tying the golden ratio to phi and Fibonacci, Leonardo Pisa or Leonardo Fibonacci wrote his book called Liber Abaci. In this book, he wrote multiple math problems. However, one of them stood out. It was about rabbits reproducing, and it asked to find the total number of pairs produced after a year. And in order to do that, you had to add the number of the pairs to the number of pairs preceding it to ultimately get the total number of the pairs. And this is, as Lily discussed earlier, the Fibonacci sequence. And just as she mentioned, if you take the ratio of the number and the number of pairs before it, it's going to ultimately converge to phi, which is also the golden ratio. However, Fibonacci did not make the connection that his sequence converges to the golden ratio. It wasn't until 400 years later that Kepler comes in and states that the Fibonacci sequence converges to the golden ratio. And this was not proved until about the 1700s by Robert Simpson. So let's discuss a bit of art and architecture. Elements, really important book, we just discussed 2 slides ago, was reintroduced in Europe in about the 1120s. And it also reintroduced the idea of the golden ratio, which became kind of like a secret science between many well-known artists like Leonardo da Vinci, Michelangelo, Raphael, and many more. However, it was Pacioli who first composed a comprehensive study of the golden ratio in his book called The Divine Proportion. And this is important because Pacioli was invited to Milan, where he ultimately meets Leonardo da Vinci, and he takes him in as his pupil and illustrator to the book, The Divine Proportion. And this is why we ultimately believe that Leonardo da Vinci incorporates the golden ratio in many of his artworks. So now we'll provide a brief history of Leonardo da Vinci. Let's talk about other works of art with Olympia.
However, one of them is a fake that does not use the golden ratio and spiral, and one of them is the real one that does use the golden ratio. So raise your hand if you think the one on the left is the original. Okay, now raise your hand if you think the one on the right is the original. If you chose the one on the right, you're wrong. I'm really sorry. In the next video I'm about to show you, you can see how the original is elongated compared to the fake, which is more condensed. So as you can see, the original follows the golden spiral compared to the fake. So the golden ratio in art is used to help map out the features and elements within different art pieces. So in addition to being used for faces, it is also used to help map out the human body and its proportions, because much of the human body follows the golden ratio. Additionally, it is used to map out architecture within art and nature within art. But why is it specifically used? The golden ratio is often used in art because it creates a sense of harmony and symmetry within the brain. And this is because images that use the golden ratio are easily processed by the eye and human brain much better than images that do not use the golden ratio. So with that knowledge in mind, we're going to take a look at a couple of paintings, and one of them will be the original with the golden ratio, and one of them will be the fake. So So first we have girl with the pearl earring. So raise your hand if you think the one on the left is the original. And raise your hand if you think the one on the right is the original. Most of you are correct. The one on the right is the original. And you can tell by her features, the one on the right is much more softer and her gaze is a lot nicer compared to the one on the left, which is more angular and sharp. Next, we have the wave of Kaginala. So raise your hand if you think the one on the right is the original. Okay. Now raise your hand if you think the one on the left is the original. Again, most of you are correct. The one on the right is the fake. You guys are really good at this, dang. The one on the left, you can tell by the wave how it is curved. It's more naturally curved compared to the one on the right. Lastly, we have Starry Night by Van Gogh. So raise your hand if you think the one on the left is the original. Okay, now raise your hand if you think the one on the right is the original. The one on the right is fake. This one I still have trouble with. It's very hard for me to tell, but if you look closely at the sky and the spirals, you can tell how they curve. It's a lot more natural compared to the one on the right. Next, Michaela will talk to you about architecture.
So, similar to artists in their artwork, architects try to incorporate the golden ratio in their designs. Ideally, they want to have a sense of harmony and balance in their buildings. The first example is the Parthenon. It's the most common example. And in between each of the columns, they create a little facade, which makes it more harmonic to the eye. The next example is the Taj Mahal. And similarly, the golden spiral is represented right here, spiral throughout. So from an outward perspective, it makes it more aesthetically pleasing to the eye. The next example is the Notre Dame Cathedral. So this is the nape, so one of the sides of the cathedral. And while it doesn't have the spiral, the ratio between the length and the width is the number of the golden ratio. And similarly, the stained glass windows throughout the cathedral also display this same number. And then the last one is the Sydney Opera House. I recently learned this, is that each of the shelves present here has the spiral, which makes it more aesthetically pleasing. And then the next one is interior design. So I won't delve into it too much, but they try to incorporate the same like balance and harmonic styles and layouts. And what they use is the 60-30-10 rule, which is also the 60-40 rule, which is a simplified version of the golden ratio. And it can be used for color schemes, patterns, layouts, furniture, decorations. And in this example, this area up here would be the 60 because it's the first thing that your eyes lay on. Down here would be the 30, and then this little area is the 10. And then, it's called the 60-40 because 30 plus 10 is 40, and then 60. And then to wrap it up, before we do, I would like 5 lucky people to volunteer. Y'all can pick. Y'all can pick. Alright.
That guy in the gray shirt. Yeah, you. Yeah, I mean, what's funny like this? You come up here. You gotta come up here.
Yeah, if you get chosen, please come up here. Graham, come up here. Eliza.
Eli, come up here.
Alright, do we have 5 people?
Is that 5? I think we need 3. 1, 2, 3, 4. And Eli.
Alright, so
Come over here.
people here, y'all get a sticky note, and your goal with the knowledge that you learned tonight is to draw your own golden ratio as close as you can to the original. You will Alright, and then we have James. Yeah. Alright, so these are the final two.
Imani and James.
Imani and James. If you think Imani, please raise your hand.
Yeah,